I'm Mugur Marculescu, founder of Magnitude Labs, where we research new AI architectures based on graph compute substrates. What you're watching is a small labeled neural network that runs on its own. It's the third one I've built with the same method. The first two, a bug brain and a robot brain, are the basis for the Labels as Computational Primitives white paper on Zendo. This one is wired up to play the ARC-AGI-3 challenge, and you just saw it solve the first level autonomously. In this video, I'll go through the motivation behind the research, the exact approach I used to build these microbrains, and how the ARC brain in particular was designed, built, and validated. I'll also be specific about what this demonstration shows and what it doesn't show or prove, because that part matters just as much. We all know that neural networks are highly competent, but you can't easily change them at runtime, and their units are unlabeled, which means their internals are very hard to understand. People usually contrast them with symbolic systems, which are readable but rigid. My thesis is that these two approaches share a single failure mode. Their units don't have grounded meaning. Graph compute substrates change how you think about that. For me, this is also personal. I think we can make AI architectures more efficient, but more than that, we need a basis for understanding how they work. That means transparency and traceability of their internal processes. I believe that's the only reliable way to build AI systems we can trust and steer, and in some real sense, give real freedom to, rather than just statistical training biases. What you're looking at is absolutely a neural network, but the way it works and the way it was built is nothing like the usual approach. These networks were not trained with gradient descent. They were compiled directly from natural language using LLMs. Every unit carries a natural language label, and that label is the specification. It implies the unit's threshold, decay, and what it should connect to. At runtime, you can see which units fire, which units they affect downstream, how the behavior aggregates, and the final effect on the system. You can also reach in and put your thumb on the scale, so to speak, on any of these neurons while the brain is running. Activation is additive, and so is suppression. So it's very easy, and it's a very interesting interactive thing to do to be able to affect the neural activations while the process is running. One key feature of the graph compute substrate is that it combines neural computation and digital computation in the same medium. So we can collect the labels of the active units as plain text and read them out through a specialized node. That gives us transparency into the system from the outside, and it gives the network the ability to introspect its own state at runtime. With the robot brain, I took that one step further. The active labels get read out into text, the text gets composed into a description of the robot's internal state, and that description goes to an image model which renders a picture of what the robot's internal world looks like at any given moment. So a linguistic model and a visual model, they're trained completely separately. They end up agreeing about the same state through their labels. To be honest about the scope here, what I have is a matched pair. The network state in the image is produced at that moment, not some deep alignment. But it is a working example of a network making sense of itself and then turning that into something a person can look at. And all of this works because both the image and the language model were trained using the same world as a prior. The name I have for the concept underneath all of this is semantic coherence. This means that in a well-formed network, the labels agree with each other and they fit together. And since the labels are neurons, it means implicitly the neural structure agrees with what it's attempting to do or solve. If you flip a sign or change a value, that coherence breaks, and the failure is visible but local. To understand what's interesting about this, I need to describe how these brains were actually built. I described the basic logic and the brain regions in natural language to a coding agent, and that coding agent, an LLM, used the graph substrate toolset to create and wire the neurons. I never touched their parameters directly. I only asked for what kinds of regions I wanted. For the ARC brain specifically, there are motor units, a very basic form of short-term memory, a rough self-model with a vague sense of where it has visited, some wall avoidance driven by a few minimal hints from a harness, a bias towards objects with a mild aversion built from just a few neurons, and a compass sense. All of these regions, for lack of a better word, were wired automatically from natural language instructions. At runtime, only the graph runs. The LLM is not involved at all, though it can absolutely monitor what is happening. In practical terms, it took me about a day to narrate the brain design, and I watched it evolve on screen. There is no compile step. It runs instantly and updates continuously as new neurons spawn or their parameters or weights are adjusted. I just kept giving instructions to steer the graph's behavior until it reached a solve rate of roughly 1 every 15 minutes on that first level. It's worth saying clearly that this little reflexive microbrain does not solve the second level. It was implicitly tuned for the first one, but it's not a random walk either. I systematically asked for changes to regions and behaviors that would encourage gliding towards goals, and the brain does have some internal sense of boredom, danger, and interestingness. Those are just neurons wired to simple mechanics like, have I made progress recently? Or, should I explore away from this wall? These microbrains may look small, but I think they're exactly the right scale to demonstrate concepts that should, in theory, scale up. The behavior is fully reflexive. There is no learning. That's not to say the brain didn't evolve. It did. It grew in front of me over that one day as I asked for modifications. But I was working at a very high level. I was observing what was happening and I asked for adjustments. That was the training. So what this demonstrates is a graph network with reflexive behavior that can solve the first level of the ARC-3 AGI challenge, all compiled from natural language with the assistance of an LLM, though that LLM is not used at runtime. There is no learning and no program synthesis at runtime. I would argue, though, that my process of giving natural language feedback was, in fact, the creation of the neural program. And that program was iterated, or rather evolved, with every instruction over the course of that day. At the very least, this shows that a supervised process like this is possible, and that neural parameters were already encoded in the LLM during its expensive pre-training. What you're watching here runs on a CPU and takes very few resources. The 2 papers behind this work are already on Zendo and linked from my personal site if you want the details. I plan to keep going on this work and see how far we can push it into the next levels of the ARC challenge.